So this is a presentation of our work in network scalable video adaptation using Big Packet Protocol. So we use Big Packet Protocol, which is one of new network protocols designed for the needs of future network architectures and new styles of applications. One of the main objectives of BPP is to provide a framework which meets the requirements of high precision services, particularly where those that have applications with specific levels of guarantees. In our mind, video, which we use here, is one of those services. Now, one of the design goals of BPP is to have an application-specific way in which individual packets or flows can use enhanced functionality built into network devices to do some kind of processing on the packet. And in particular, with BPP, the strategy is not to see whole packets being dropped, rather parts of the packets, which are called chunks, being dropped from the packets. So the packet size is adapted to make it smaller rather than dropped completely. And this chunk elimination is done by observing the network conditions and taking into account some application metadata that is embedded in the packet by the sending application. And the main concept is to reduce the load on the network, but still deliver packets, but reduce the consumed bandwidth, with the goal to have no stalling at the receiver. And to make Big Packet Protocol effective for continuous media, Big Packet Protocol needs to be coupled with an encoder and a decoder that is amenable to having chunks dropped. And in this case, it's doing multiple encodings for the same region of the video, the same frame. So these multiple encodings can be put into a packet in a very specific way. And if any of the chunks are dropped in the network, then the receiver will still have some video data. And by using layered video encoding, the video file can be encoded such that the encoded file contains a base layer and a number of enhancement layers. Okay, so this layered video we can see is very compatible with the packet modification techniques that BPP provides, and it allows a network node to delete some parts of the packets, in this case chunks that hold the enhancement layers, but always keep the base layer. So even if a packet arrives at a bottleneck during its journey and chunk deletion is necessary, we always send something to the client. So BPP itself supports a number of commands, but we only use one called packet wash in this work, and that packet wash is the command that eliminates chunks from packets during transmission. And in packet wash, chunks that have low priority can be dropped, and those that with higher priority can be kept. And the sender can inject priority levels for different chunks as it creates the packet with the knowledge of the content that it's actually sending. And we'll demonstrate this packet wash during the middle of the video demo. So, although the information for guiding the network nodes as to which chunk can be removed, it's also necessary to add more fields to support layered video, because there's more information that video contains than some more simplistic applications. And in our case, we have a significance value which holds the importance of the chunks, and condition value, which can define some conditions related to the chunk removal. And the significance values in each packet are set by considering the video stream and the temporal layer, whether it's an iframe, a p frame, some other information that we have, and considering that impact on the quality of experience. So let's have a closer look at what we've been building. We've successfully taken these concepts that have just been described, and we've built a working proof of concept that will be demonstrated. Now, one of the most important aspects is to look at the mechanism by which video frames from the different layers of the video are mapped and placed into these BPP packets. And what we see in the figure is that a sequence of layers, layer 0, layer 1, layer 2, for a particular frame are actually multiplexed into a set of packets. So if we look at the figure, we can see, although we have layer zeros before layer 1, before layer 2, what we actually do is we take a number of bytes from each of the layers and we put them into a packet. And then we keep doing that until all the layers are consumed for a particular frame. And what happens during transmission, if the network is busy, then the chunks that contain layer 2, the green blobs, will be eliminated, but the packets will still carry on with layer 0 or layer 1. If it's very congested or very busy or there's limited bandwidth, then layer 1 and layer 2 can be eliminated, and we always receive a packet containing layer 0, which the receiver can decode and play out. And so you don't get these large dropouts or large delays. So in our preliminary experiments, we did a number of analyses of different network protocols and different transmission techniques. And in particular, we compared using BPP and UDP, and the results of those are in tables in the paper, and I won't go through them now, but please have a read of them if you're interested. But the important thing is that when using BPP and layered video transmission, the clients do receive a continuous stream of playable video, and so we have low levels of outage, okay, at the client. And what we observed is that BPP provides a higher effective bandwidth utilization than UDP, for example, because we don't have wasted packets that are associated with layers that cannot be played. With UDP, we have random dropouts, the packets arrive, and the client has to reconstruct the layers and the frame from these random packets. And what we found with low bandwidth is that many of the packets are basically unusable, and therefore we've wasted bandwidth by sending packets that can't be used. With BPP, we rarely see this situation, and this is why we say we have higher effective bandwidth utilization. So here are some figures from the paper. Try to highlight what I was just mentioning. The left figure shows a situation where we dynamically increase the bandwidth of the link as we send the video. And what we see is many packets that contain layer 0. And then as the bandwidth increases, we add some layer 1s. Some of them might not be usable, but the percentage of unusable ones is very, very low. As we get more and more bandwidth, more of the layers are usable. If we look at the UDP case for the increasing bandwidth, we see quite a dramatically different pattern. So what happens with UDP is the sender sends UDP packets, the network link gets filled up with stuff, then you get lots of dropout because the link's congested, then it tries to send some more, and you get this cycle of send, drop, but there's no coherence or consistency to the delivery. And this is what I was trying to highlight. If we look at these graphs from the measurements that we did from the received packets at the receiver, we have a bar graph showing the number of valid frames received, lost frames, and unusable frames. And you'll see for various bandwidths from 0.3 up to 1.4 megabits, including ascending bandwidth, where we give more bandwidth over time, or descending, where we decrease the bandwidth over time. You'll see with BPP, it's consistently receiving valid frames. Might not receive all the layers, but we always get valid frames. If we go over to UDP, we'll see that the percentage of valid frames varies. But what we'll also see is there's lost frames. Data arrives sometimes, so we have these unusable frames. The yellow is the just loss in the network. And so you see a very different pattern of what's going on given the different protocols and the network dynamics. So let's have a closer look at what the demo will show. In our mind, the work clearly demonstrates that using scalable video coupled with big packet protocol and using this packet wash mechanism inside the network node, we are actually able to implement an in-network video adaption scheme, which can change the video characteristics as the data on the server is not always the same as data at the client. Okay, so if you look at what gets sent and what gets received, they can sometimes be different if the bandwidth is not good enough to transmit all of it. However, we still get good quality of experience attributes at the client. And in the demo, you'll see that the server and the client will be connected using some virtualized network with soft routers. And we've programmed a network function to do the BPP behavior in the node and to look at the chunks, look at the condition, the significance value that I mentioned earlier, and actually drop some of the chunks. Okay. And what we'll see is that the packet size definitely changes in the face of congestion. We'll demonstrate that by sending some videos, and we can change the bandwidth for different tests. And we'll also see, as we've been highlighting, that video data will arrive at the client. So this figure here gives an overview of the setup that we've built. We have this video aware process running in the network nodes. So the server, the transmitter, is BPP aware. It takes an SVC video stream, H.264 layered video, and it constructs a sequence of packets multiplexed from the layers, as highlighted earlier. And we get this stream of packets with the different layers. It goes through the network. When we get to a BPP aware video process as a network function, if it sees limited bandwidth, it can eliminate the chunks. The packet still gets forwarded, but with less data, and the client will receive the video. And as I said, we'll see that demonstrated clearly when we run the live demo. So in conclusion, what we've found is that this new transport layer protocol called BPP is very amenable to video streaming if you choose the right encoder and decoder, okay? And the layered encoder will provide each packet containing all of the encodings in the frame from the base layer upwards, but spread out across a set of packets. And as we've said a few times, this BP aware network node can drop the chunks if necessary. And finally, the results have shown that even when there's no approaches on the client side, as you can see in some other schemes at the application layer, such as client-side quality adaption, using BPP and SVC with a suitable chunk removal approach provides very high quality of experience. and we'll show that the network resources were used effectively. Okay. And for a full working system, we would need to connect a live SVC encoder directly to a BPP packet constructor in the server. And at the client end, we need a live decoder that can read BPP packets from the network and recreate this SVC stream and feed that into a real-time decoder. And in the future, we'd like to use these techniques and have a look at things like H.266 VVC encoders, because at the moment we're only using H.264. But overall, we've found that the work has been a success, and we're very happy with how the work has gone and the results that we've got. So this is the end of the talk. Thank you very much.